Imagine you're working on a crucial group project. Right. And everyone is trying to update the exact same shared document at the very same moment.
Yeah, or like maybe two people trying to deposit money into the same bank account simultaneously.
Exactly. What happens? Chaos, right? Data gets corrupted, intentions are lost, and suddenly your, meticulously planned work is just a digital mess.
And that's not just a headache for us humans. In computing, this isn't just a possibility, it's like a fundamental challenge. When multiple processes or threads try to access and modify the same shared data, well, that exact kind of digital chaos can erupt.
Right. So today on the deep dive, we are plunging headfirst into synchronization tools. These are the clever, often invisible mechanisms operating systems use to ensure order and, well, prevent that precise kind of digital meltdown.
Yeah, our mission for this deep dive is really to unpack how operating systems manage this concurrent access to shared data. We'll explore what happens when they don't manage it properly, which can be messy.
Oh, I bet.
And then we'll reveal the, frankly, ingenious solutions that have been developed over decades. We're talking low-level hardware tricks all the way up to high-level programming constructs.
And we'll even look at some real-world failures and successes, right? Like that Mars mission story.
Yeah, definitely. That's a fascinating one. Shows just how critical this stuff is.
Okay, so let's unpack this. Where do we start? Maybe at the very root of the problem. What causes this digital chaos?
Good place to start. It often comes down to something called race conditions.
Race conditions.
Right.
Yeah.
We're talking about what are called cooperating processes or threads. These are, parts of a program that can affect or be affected by others, usually because they share a common memory space or they pass data back and forth.
And the big challenge here is data inconsistency. That sounds bad.
It is. When multiple processes access and modify the same data concurrently, the final outcome can become unpredictable and critically incorrect.
Okay, so how does it actually play out? Can we make it more concrete?
Absolutely. Let's revisit a classic scenario. The producer-consumer problem. Remember the bounded buffer?
Vaguely, yeah. Producer adds stuff, consumer takes stuff out, limited space.
Exactly. Now, imagine we add a simple integer variable, let's call it count, just to track how many items are in the buffer. The producer increments count plus plus, when it adds an item.
And the consumer decrements it, count, when it removes one. Seems straightforward.
It sounds perfectly logical, doesn't it? If count is 5 and the producer adds an item, it should become 6. If a consumer removes one, it should become 4.
Makes sense.
But here's the aha moment of a race condition. Imagine count is 5. The producer runs count plus plus, and at basically the exact same time the consumer runs count. What do you expect count to be after both operations?
Still 5. One added, one removed.
That's the logical expectation. But, and this is the kicker, because count plus plus and count aren't single uninterruptible actions at the machine level.
Okay. They're multiple tiny steps.
Precisely. They involve multiple tiny machine-level instructions. And because of that, count could surprisingly end up as 4, 5, or even 6.
Oh, wait. How can it be 6 or 4?
Well, think about count plus plus got. It's not just one magical step. It might involve, say, 1, load count from memory into a temporary CPU register. 2, add 1 to that register. 3, store the new value from the register back into count in memory.
Okay, 3 steps.
And count is similar. Load, decrement, store. Now, the danger is that the operating system can interrupt or preempt one process right in the middle of these tiny steps.
Oh, so like after step 1 but before step 3.
Exactly. So imagine count is 5. Producer loads 5 into its register, step 1, increments it to 6, step 2. But before it can store that 6 back to memory, step 3, boom, OS switches to the consumer.
Okay, so the producer's register has 6, but memory still says 5.
Right. Now the consumer runs. It loads count from memory, which is still 5, into its own register. It decrements it to 4 and writes that 4 back to memory.
Memory now holds 4.
Then eventually, the OS switches back to the producer. The producer just picks up where it left off, which was step 3. Store its register value, which is 6, back to memory. So the final value is 6.
Even though 1 was added and 1 was removed, and if the consumer wrote last, it could be 4. Wow.
Exactly. This situation, where the outcome depends entirely on the unpredictable timing and order of execution, that is a race condition.
Okay, that makes the name make sense. They're racing, and the outcome is uncertain.
And this isn't just some theoretical edge case. These scenarios are incredibly common inside operating systems themselves. Think about managing shared resources, like the list of open files or maybe the next available process ID when you fork a new process.
Right, you mentioned process IDs earlier.
Yeah, if two fork calls happen concurrently without protection,
Hmm.
they could both read the same next available, increment it locally, and then both try to assign the same ID to two different processes. Big problem.
Especially with modern multi-core systems, right, where lots of things are truly running in parallel.
Absolutely. Multi-core makes these race conditions much more likely and much harder to track down.
So this leads us to the whole idea of the critical section problem. How do we solve this?
Right. We define a critical section as that segment of code where a process is messing with shared data, accessing, updating, whatever.
And the core idea is only one process in its critical section at a time.
That's the heart of it, mutual exclusion. We need a protocol, a set of rules. Typically, a process has an entry section code to request permission to enter, then the critical section itself, then an exit section to clean up or release whatever allowed it in, and finally the remainder section, which is just the rest of its non-critical code.
Okay, entry, critical, exit, remainder. Got it.
Yeah.
And you mentioned rules or requirements for any good solution.
Yes, three fundamental requirements. Any valid solution must satisfy these. First, mutual exclusion. We just talked about it. If one process is in its critical section, no others can be in theirs. Bedrock principle.
Makes sense. Can't have two people changing the shared document at once. What's number two?
Second is progress. This means if nobody is currently in a critical section and some processes want to get in, then the decision about who gets in next can't be postponed indefinitely.
Yeah.
And importantly, only processes that actually want in and are busy doing other non-critical stuff get to participate in that decision.
So things have to keep moving. If the door's open and people are waiting, someone has to be chosen to go in reasonably quickly.
Exactly. No getting stuck forever outside if it's available. And third, bounded waiting.
Bounded waiting. Like there's a limit.
A limit on how unfair things can be. There must be a bound on the number of times other processes are allowed to enter their critical sections after a process has made a request to enter, but before that request is granted.
Ah, so you can't have one process just constantly getting pushed back in line while others keep cutting in front indefinitely.
Precisely. It guarantees you'll eventually get your turn.
Mm.
Mutual exclusion, progress, bounded waiting. Those are the three pillars.
And you said these aren't just for our apps, they happen inside the OS kernel too, like with that process ID example.
Definitely. Kernel data structures are prime candidates for race conditions. Lists of open files, memory allocation structures, process scheduling queues, that next available tumpets. Lots of shared stuff the kernel manages.
So how did OS designers first try to tackle this, especially back in the day?
Well, on older single-core systems, one early approach was pretty brute force.
Yeah.
Just disable interrupts entirely while modifying shared kernel data.
Ah, turn off the thing that lets the OS switch processes?
Exactly. If you prevent interrupts, the current sequence of kernel instructions runs to completion without being preempted. No other code runs, so no race condition on that shared data. Simple, effective, on one core.
But not on multi-core systems, you mentioned.
Right. It falls apart there. So disabling interrupts on all cores requires sending messages between them, which is slow and complex. Plus, if the system clock relies on interrupts, which it often does, disabling them messes up system timing. It's just not practical or efficient for modern hardware.
So that simple trick is out? This must influence how kernels are designed then.
It does. It leads to a distinction between preemptive and non-preemptive kernels. A non-preemptive kernel won't allow a process running in kernel mode to be interrupted. It runs until it exits kernel mode, blocks waiting for something, or voluntarily gives up the CPU.
So simpler for race conditions inside the kernel, since only one thing is active in the kernel at a time.
Essentially, yes.
Yeah.
Much simpler from a concurrency perspective. But the downside is responsiveness. A long-running kernel task can make the whole system feel sluggish.
And a preemptive kernel.
A preemptive kernel does allow preemption, even when a process is running in kernel mode. This makes the system much more responsive, which is crucial for things like real-time applications. But
it makes designing the kernel harder because you have to worry about all those race conditions again right inside the OS code.
exactly. You need careful locking and synchronization within the kernel itself. It's a trade-off between simplicity and responsiveness.
Okay, so if disabling interrupts isn't the way on modern systems, what about pure software solutions? Did anyone figure that out?
Well, there were attempts. One classic, really elegant one is Peterson's solution. It's taught a lot because it's a clever demonstration of logical reasoning.
But you sound hesitant. Does it actually work today?
That's the crucial caveat. Peterson's solution is not guaranteed to work correctly on modern computer architectures, but understanding why it fails is super important.
Okay, intrigued. Tell me about Peterson's first, then why it breaks.
So Peterson's was designed for just two processes, let's call them P0 and P1, wanting to access a critical section. It uses two shared variables, an integer turn, indicating whose turn it is, and a Boolean array flag2, where flaggy being true means process pi is ready to enter.
Kernel and flag, okay.
The logic roughly is, process pi sets its flaggy to true. Then it sets turn to j, the other process, giving the other process priority. Then it enters a loop, waiting as long as the other process's flag is true and it's the other process's turn.
So it waits only if the other process is also ready and it's currently the other's turn.
Right. This combination cleverly ensures mutual exclusion, progress, and bounded waiting. In theory, it was a beautiful piece of software logic for its time.
It does sound elegant. A pure software fix. So what's the catch? Why doesn't it work reliably now?
The catch is a fundamental aspect of modern hardware and compilers. Instruction reordering.
Instruction reordering, you mean the CPU or the compiler changes the order of my code?
Exactly. For performance reasons, they can reorder read and write operations if there aren't direct data dependencies between them. For a single thread, the end result is usually the same, so it's fine.
But for multiple threads sharing data, oh boy.
Yeah, it can break everything. Let me give you a really clear example. Imagine you have a Boolean flag, initially false, and an integer x, initially 0.
Okay, flag and x.
Thread 1 runs this code, while .flag, print x. So wait until flag is true, then print the value of x.
Simple enough, expecting to print whatever thread 2 sets x to.
And thread 2 runs this, x100, flag is true, sets x, then sets the flag.
So thread 1 should print 100, right?
You'd absolutely think so. But what if the processor or compiler reorders thread 2's instructions? What if it executes flag use true before x equals 100?
Oh, then thread 1 sees flag become true, exits its loop, prints x, which might still be 0.
Exactly. Or even stranger things can happen with how reads and writes are buffered and made visible across cores. This reordering completely undermines the assumptions Peterson's solution relies on. Its careful logic about setting flag then turn can be rearranged, potentially allowing both processes into the critical section.
Wow, so performance optimization breaks the synchronization logic.
That's the core issue. Purely software-based solutions like Peterson's just aren't robust enough against these modern architectural behaviors. We need guarantees. We need hardware help.
Okay, so that brings us squarely to hardware support for synchronization. If software alone isn't enough, what does the hardware give us?
Right. Reliable solutions almost always lean on some hardware support. One key concept here is the memory model of the architecture.
Memory, what does that define?
It defines the rules about how memory writes by one processor become visible to other processors and in what order. Some architectures have strongly ordered models, where things are pretty intuitive. Writes become visible quickly and in order.
In others.
Others have weakly ordered models, where writes might be buffered or reordered, and visibility is intermediate. This gives hardware designers more flexibility for performance, but it makes the programmer's job harder. You can't assume writes appear instantly everywhere.
So how do you force order when you really need it, like in synchronization code?
That's where memory barriers or memory fences come in. These are specific machine instructions that tell the processor, okay, stop, make sure all previous memory operations are completed and visible everywhere before proceeding past this point.
Like putting up a temporary roadblock for memory operations.
Kind of, yeah. It enforces an ordering point. If we put memory barriers in that flag, an X example, thread 2 would have X100, memory barrier, flag true. This ensures X100 is visible before flag becomes true.
So barriers fix the reordering problem for specific cases. But are there more direct hardware tools for locking?
Absolutely. The most fundamental are atomic hardware instructions. The key word is atomic, meaning the operation happens as one single, indivisible, uninterruptible unit. It either completes fully or not at all. No half-done states.
Okay, atomic, like it can't be interrupted midway.
Exactly. Two classic examples are test and set and compare and swap, or CAS.
Yes. Tell me about test and set.
It's pretty simple. It reads the current Boolean value of a target memory location, returns that original value, and then atomically sets the memory location to true.
Returns the old value, sets it to true. How's that used for locking?
You can use a shared Boolean variable, say lock, initialized to false. To acquire the lock, you loop, calling test and set. If it returns false, it means the lock was free, and you just atomically set it to true, so you got the lock. If it returns true, the lock was already taken, so you loop again.
Okay, simple check and set loop. What about compare and swap? You said CAS.
CAS is more powerful and generally more useful. It takes 3 arguments: a memory location value, an expected value, and a new value.
Okay, value expected.
It atomically does this.
Yeah.
Checks if the current content of value is equal to expected. If yes, it updates value with new value. Regardless of whether the update happened, it always returns the original value that was in value before the operation.
Okay. Check if match is expected. If so, update, return the original. How does that give us a lock?
Similar idea, use a shared integer lock, initialized to 0. To acquire, you call compare and swap lock 0, 1.
Trying to swap 0 for 1.
Right. If CAS returns 0, it means lock was 0, the expected value, and it successfully changed it to 1, the new value. You got the lock. If it returned the 1, it means someone else already set it to 1, so you didn't get the lock, and you try again or wait.
So CAS seems more flexible because you specify the expected value.
Exactly. And CAS is incredibly important. It's the primitive building block for implementing many other synchronization mechanisms, including things like lock-free data structures and atomic variables. There are even ways to use CAS to build locks that satisfy all 3 critical section requirements, including bounded waiting, though the algorithm gets a bit more complex.
You mentioned atomic variables built on CAS.
Yeah. Modern programming languages and libraries often provide atomic variables. These wrap basic types like integers or booleans and provide operations like increment, decrement, compare and set, etc. They're guaranteed to be atomic. Under the hood, they typically use CAS or similar hardware instructions.
So for our count ++ race condition earlier, we could just use an atomic integer for count.
Precisely. You'd call atomic increment and count. The library hardware ensures it happens atomically, solving that specific race condition without needing an explicit lock.
That sounds way easier. Are locks obsolete then?
Not quite. Atomic variables are great for single variable updates, but they don't magically solve all synchronization problems, especially those involving multiple variables or more complex conditions. Remember the producer-consumer buffer?
Yeah.
Imagine the buffer is empty, count is 0. Then the producer adds 1 item, count becomes 1. If 2 consumers were waiting, an atomic increment might wake them both up. Both might then check the now non-zero count, both try to consume the single item, and you'd have a different kind of error. You still need higher-level coordination.
Ah, okay. So atomics help with simple updates, but not complex logic, which brings us to the higher-level software tools, like locks.
Exactly. The most common are mutex locks, short for mutual exclusion locks. They're probably the simplest high-level tool.
How do they work?
Super simple concept.
Yeah.
You have a lock object. Before entering a critical section, a process must call acquire on the lock. If the lock is available, acquire succeeds, and the process holds the lock. If it's already held by another process, acquire blocks or waits until it's free.
Okay, acquire before and then.
Then you execute your critical section. When you're done, you call release on the lock, making it available for other waiting processes. Acquire, critical section, release. That's the pattern.
How does acquire typically wait if the lock isn't free? Does it just sit there?
Well, one way is busy waiting. The acquire call just sits in a tight loop, constantly checking if the lock is available. This is often called a spinlock.
Spinlock. Sounds wasteful, just burning CPU cycles, doing nothing but checking.
It definitely is wasteful on a single core system. The spinning process is using the CPU when another process, maybe the one holding the lock, could be running.
But you mentioned spinlocks earlier. They do have advantages sometimes.
On multi-core systems, yes. The main advantage is avoiding the overhead of a context switch. A context switch saving one process's state, loading another's takes time. If a lock is typically held for a very short duration.
Shorter than the time it takes to switch out and switch back in.
Exactly. If the lock is held for, say, less time than 2 context switches would take, it can actually be faster for a waiting thread to just spin on one core, while the thread holding the lock finishes quickly on another core. No OS intervention, no switching overhead. So spin locks are often used for short-duration locks inside the OS kernel or performance-critical libraries on multi-core machines.
Okay, so mutexes are simple locks, sometimes implemented with spin locks. What else is in the toolbox?
Next up, we have semaphores. These are a bit more versatile and were introduced way back by Edsger Dijkstra.
Dijkstra, famous name. How do semaphores work?
A semaphore is essentially an integer variable, but you can only access it through 2 special atomic operations.
Yeah.
Wait, S, and signal, S. Historically, these are called P and V.
Wait and signal, what do they do?
Wait
Yeah.
conceptually works like this. It checks the semaphore value S. If S is positive, it decrements S and continues. If S is 0 or negative, it waits until S becomes positive, then decrements and continues.
Waits if it's not positive, decrements if it is.
Okay, and signal S. Signal S simply increments the semaphore value S. Both wait and signal have to be atomic operations themselves.
So how are these used? Are they just like mutex locks?
They can be used like mutex locks. If you initialize a semaphore to 1, it behaves like a mutex. This is called a binary semaphore, value 0 or 1. Wait,
Yeah.
acquires the lock, signal, releases it.
That can be more than one.
Yes. That's the power of counting semaphores. Their value can be any non-negative integer, or sometimes even track negative values in implementations. They're great for controlling access to a finite pool of resources.
Licenses for software or
Yeah.
printers.
Perfect examples. If you have, say, 5 licenses for some software, you initialize the semaphore to 5. Each process wanting a license calls wait. If the count is positive, it gets a license. Count goes down. If it's 0, it waits. When a process is done, it calls signal, incrementing the count, potentially allowing a waiting process to get a license.
That's neat. Controlling a number of resources, can they do other things?
Yeah, they're also used for general synchronization between processes. Say you need statement S2 in process P2 to run only after statement S1 in process P1 finishes.
How would you do that?
Use a semaphore, let's call it cinch, initialized to 0. Process P2 calls wait, cinch, right before S2. Since cinch is 0, P2 waits. Process P1 executes S1 and then calls signal, cinch. This increments cinch to 1, allowing P2 to pass its wait. Call and execute S2.
Ah, using the wait signal to pass a baton, essentially. But wait, if the semaphore value is 0 or negative, the process waits. Does that mean busy waiting again, spinning?
That's the naive definition.
Yeah.
But no, modern implementations are smarter. Instead of busy waiting, if a process calls wait and finds the semaphore value isn't positive, the OS can suspend that process.
Suspend it, like put it to sleep.
Exactly. The process's state is changed to waiting and is placed on a queue associated specifically with that semaphore. The CPU scheduler then picks another process to run. No wasted CPU cycle spinning.
Okay, that's much better. So what happens when someone signals?
When another process calls signal S, the OS increments S. If S was negative or 0, meaning processes were waiting, the OS picks one process from that semaphore's waiting queue, changes its state back to ready, and puts it back on the general ready queue to be scheduled later. This is often called a wake-up operation.
So wait can lead to sleep, and signal can lead to wake up. Much more efficient.
Definitely. Though it's important to remember that the wait and signal operations themselves still need to be atomic, especially the parts that modify the semaphore value and check the queue. On multi-core systems, this often requires using those low-level hardware spinlocks, or CAS, internally for very short periods just to protect the semaphore's internal state.
Okay, semaphores seem powerful, but are they easy to use correctly?
Ah, that's the rub. While powerful, semaphores are notoriously tricky to get right. It's easy for programmers to make mistakes.
Like what kind of mistakes?
Oh, classic ones. Forgetting to call wait before accessing the shared resource. Forgetting to call signal after you're done, which could lead to deadlock if others are waiting. Calling signal when you shouldn't. Accidentally calling wait twice, potentially causing deadlock for yourself.
Yeah. Simple mistakes with big consequences and hard to debug.
Incredibly hard. These timing errors might only show up under very specific interleavings of threads, making them non-reproducible and a nightmare to track down.
So is there something safer,
Uh-huh.
easier for the average programmer?
Yes. This difficulty led to the development of monitors, which are a higher-level synchronization construct designed specifically to reduce these kinds of errors.
Monitors, how do they improve safety?
Think of a monitor like a special kind of module or class. It bundles together the shared data and the procedures or methods that operate on that data. The key feature is the monitor implicitly guarantees mutual exclusion for all its procedures.
Implicitly, meaning the programmer doesn't have to add, acquire, and release calls.
Exactly. The compiler or runtime system enforces it. Only one process can be active, executing any code inside the monitor at any given time. If a process calls a monitor procedure and another process is already executing inside, the calling process automatically waits outside.
Oh, that sounds much safer. Takes the burden of manual locking off the programmer for simple mutual exclusion.
It really does. It eliminates many common errors related to forgetting locks or releasing them incorrectly. The shared data is protected within the monitor's walls.
But what if a process inside the monitor needs to wait for something specific, Like in our buffer example, the consumer needs to wait if the buffer is empty. It's already inside the monitor, so another process can't get in to produce anything.
Great question. Monitors alone only provide mutual exclusion. They need an additional mechanism for processes to wait for specific conditions while inside the monitor, and crucially, to temporarily release the monitor lock so other processes can enter. This mechanism is called condition variables.
Condition variables. Okay, how do they work?
Inside a monitor, you can declare condition variable, say x. If a process is executing inside the monitor and finds it can't proceed, e.g. buffer is empty, it can call x.wait.
What does x.wait do?
It does two things. One, it immediately suspends the calling process. Two, it releases the implicit monitor lock, allowing another process to potentially enter the monitor.
Ah, so it waits and lets someone else in. Clever. How does it get woken up?
Another process, executing inside the monitor later, might make the condition true. Example, adds an item to the buffer. That process can then call x.signal.
An X signal wakes up a waiting process.
It wakes up exactly one process that is currently suspended on x.wait. If multiple processes are waiting on x, only one gets woken up. The choice might depend on the implementation, maybe FIFO. If no processes are waiting on x, then x signal does absolutely nothing.
Nothing. That's different from a semaphore signal, which always increments the count.
Right. It's a key difference. X signal is a hint. Hey, the condition you might be waiting for might now be true. Check again. It doesn't carry state like a semaphore count. This prevents certain kinds of errors. The woken process then implicitly reacquires the monitor lock before it continues execution from where it called x.wait.
Okay, monitors with condition variables sound like a pretty robust combination, safer than raw semaphores.
They generally are, promoting a more structured way to handle concurrent access. Though, like any tool, they aren't foolproof.
How so? What can still go wrong?
Well, the monitor guarantees mutual exclusion for its internal procedures. But it can't stop a programmer from, say, accessing the shared resource directly without going through the monitor, if the language allows it, or forgetting to signal a condition when it becomes true, or calling monitor procedures in the wrong order. The structure helps a lot, but logical errors are still possible.
Right, it helps with locking, but not overall program logic necessarily. Okay, we've covered correctness, mutual exclusion, progress, bounded waiting. But you mentioned things can still go wrong even if the locking is technically correct. Something about liveness.
Yes, liveness. This moves beyond just getting the right answer to ensuring that processes actually make progress and don't end up stuck waiting forever for something that will never happen. Liveness failures mean the system isn't really living up to its potential.
And what are the common ways liveness fails?
Two big ones are deadlock and priority inversion.
Deadlock? That sounds ominous. Like gridlock.
Pretty much the computing equivalent.
Yep.
It happens when two or more processes are blocked indefinitely, each waiting for a resource that is held by another waiting process in the set.
Can you give an example?
Classic example uses two semaphores, S and Q, both initialized to 1, like mutexes. Process P0 does wait S, wait Q, signal S. Process P1 does wait S, signal Q. They acquire the locks in opposite orders. Uh-oh is right. What if P0 successfully executes wait and acquires S? Then the OS switches to P1. P1 successfully executes wait, Q, and acquires Q. Now P1 tries to execute wait S, but S is held by P0, so P1 blocks. The OS switches back to P0. P0 tries to execute wait, Q, but Q is held by P1, so P0 blocks.
And now P0 is waiting for P1, and P1 is waiting for P0. Neither can release the lock the other one needs. They're stuck forever.
That's deadlock, a circular wait dependency.
Nasty. Okay, what's the other one? Priority inversion.
Priority inversion is more subtle. It's a situation where a lower priority process holding a lock or resource needed by a higher priority process gets preempted by a medium priority process.
Hang on. High needs something low has, but medium jumps in and stops low from running.
Exactly. Let's say you have three processes: L, low priority; M, medium; and H, high. H needs resource R, currently held by L. Normally, H would just wait for L to finish with R.
Okay, H waits for L.
But now, process M becomes ready to run. Since M has higher priority than L, the OS preempts L and runs M process L, which holds the resource H is waiting for, is now stuck, unable to run.
And H is still waiting for L, but L can't run because M is running. So effectively, the medium priority process M is indirectly blocking the high priority process H.
Precisely. The duration H has to wait is no longer just dependent on how long L holds the resource, but potentially on how long M and any other medium priority processes run. This inverts the expected priority scheme.
Is this just theoretical, or does it happen in real systems?
Oh, it's very real. It famously caused major problems for NASA's Mars Pathfinder mission back in 1997.
The Mars rover, what happened?
The Sojourner rover's computer system kept experiencing total system resets, seemingly randomly. They eventually traced it back to priority inversion. A high-priority task, like managing the communication bus, needed a mutex lock held by a low-priority task doing meteorological data gathering. But frequently, several medium-priority tasks, like data processing, would become active and preempt the low-priority task while it held the lock. A high-priority bus task would then block, waiting for the lock. If it waited too long, a watchdog timer would assume the system had hung and trigger a full reset to recover.
Wow. So medium priority tasks were indirectly causing system resets on Mars by blocking a low priority task holding a critical lock. How did they fix it?
They used a technique called the priority inheritance protocol. With this protocol, if a high-priority task needs to wait for a resource held by a low-priority task, the low-priority task temporarily inherits the high priority.
So L temporarily becomes H's priority.
Exactly. In the Pathfinder case, the low-priority meteorological task inherited the high priority of the bus task. This meant the medium-priority task could no longer preempt it. The low-priority task finished quickly with the mutex, released it, dropped back to its normal priority, and the high-priority bus task could then acquire the lock and proceed without timing out.
And they uploaded this fix to Mars.
Yep. They remotely patched the software using this priority inheritance mechanism, and the reset problem vanished. A fantastic real-world example of why understanding these synchronization issues is critical.
Absolutely incredible story. Okay, so we've seen hardware primitives, software algorithms like Peterson's and its flaws, mutexes, semaphores, monitors, and these liveness issues like deadlock and priority inversion. That's a lot of tools. How do developers actually choose which one to use? Is there a single best tool?
Yeah, that's the million-dollar question. And the answer is there's no single best tool. It really depends on the specific scenario, the hardware, the contention level, the complexity needed.
So it's about trade-offs.
Always trade-offs. Remember, those low-level hardware instructions like compare and swap are often the fundamental building blocks underneath everything else.
Right, CAS.
And there's a whole area of lock-free algorithms that try to use CAS directly to manage shared data without traditional locks. These are often optimistic.
Optimistic, like hope for the best.
Kind of. You try to perform your update using CAS, assuming you won't collide with another thread. The CAS operation itself tells you if you succeeded, because the value was what you expected, or if someone else changed it in the meantime, the value wasn't what you expected. If you failed, you typically retry the whole operation.
Contrasted with pessimistic locking, where you acquire a lock first, assuming contention might happen.
Exactly. Lock-free has benefits potentially lower overhead, better scalability, no deadlock from locking, but they're notoriously difficult to design and test correctly.
Okay, so lock-free is an advanced option. What about the performance of traditional locks versus something like CAS under different conditions?
Good question. Under low or no contention, when threads rarely collide, both traditional locks and CA-based approaches, like spinlocks or atomic variables, are very fast. CAS might be slightly faster as it avoids some locking overhead.
What about when things get busier, moderate contention?
Under moderate contention, CAS often pulls ahead. Why? Because the optimistic approach often succeeds on the first or second try, avoiding the relatively high cost of putting a thread to sleep and waking it up later, context switching, that happens with blocking mutexes or semaphores.
But if there's lots of contention, everyone trying to access the same thing constantly,
Then, perhaps counterintuitively, traditional blocking synchronization, mutexes, semaphores that use sleep-wake-up, can become faster again. Under high contention, the cost of repeated spinning or retrying with CAS becomes very high. You're just wasting CPU cycles, failing over and over. Putting threads to sleep until the resource is free becomes more efficient overall.
So the optimal choice depends heavily on how much fighting there is over the resource.
Absolutely. And for specific use cases, simple counter updates. Atomic integers are usually much lighter than a full mutex. Need a lock for a very short time on a multi-core system? A spin lock might be best. Need basic mutual exclusion for a critical section? A mutex lock is often clearer and preferred over a binary semaphore. Need to control access to end resources? Accounting semaphores a natural fit. Want higher level safety and structure? Bundling data and operations. A monitor is a good choice, though maybe with slightly more overhead.
It really is a whole toolbox, and you need to pick the right wrench for the job.
That's a great analogy. And the field is always evolving. There's constant research in compilers, programming languages, hardware, and APIs to make concurrent programming easier, safer, and more efficient.
Wow, we've really gone deep today. From the chaos of race conditions to the elegant, if sometimes flawed, solutions like Peterson's, the hardware foundations, and the higher level tools like mutexes, semaphores, and monitors, plus the dangers of deadlock and priority inversion, it's clear how absolutely essential synchronization is. It's the hidden choreography, turning potential digital chaos into ordered, predictable execution.
It truly is. But as we saw, it's such a delicate balance, getting the locking right for correctness, ensuring progress so things don't stall, and avoiding those little pitfalls.
Which leaves us with a final thought for you, our listeners. We've seen the tools and the challenges. So think about this. What kinds of really complex systems out there, maybe smart city infrastructure, massive cloud platforms, intricate scientific simulations might benefit most from synchronization solutions that are custom tailored, going beyond the standard tools? And how much more efficient or reliable could those systems become if we got that synchronization just right?
Yeah, something to ponder. The impact could be huge.
We really hope this deep dive into synchronization tools has given you a clearer understanding of this critical, often hidden aspect of computing. Keep that curiosity burning.
From all of us on the Deep Dive team, thank you so much for joining us. Until next time, keep learning.